Here's a video for 9-6 comparing two samples. So here's an example. It says, how quickly do synthetic fabrics such as polyester decay in landfills? A researcher buried polyester strips in the soil at different lengths of time, then dug up the strips and measured the force required to break them. Breaking strength is easy to measure and is a good indicator of decay. Lower strength means the fabric has decayed. For one part of the study, the researcher buried 10 strips of polyester fabric in well-drained soil in the summer. The strips were randomly assigned to two groups. 5 of them were buried for 2 weeks and 5 were buried for 6 weeks. Here are the breaking strengths in pounds. So as we can see here, for the 2-week group, this is the amount of pounds it took to break the polyester. For the 16-week group, this is the amount of pounds it took to break the polyester. So it says, do the data give convincing evidence that polyester decays more in 16 weeks than in 2 weeks? All right, so this is a two-sample mean problem because we are comparing two groups and its means because our data is quantitative. So first thing we're going to do is identify our symbols. So since we have two different populations, we're going to have two sets of symbols. So first, starting with group 1, which is the 2-week group, n is equal to 5. We're going to put the data into GeoGebra, as we can see here. Okay, there's no outliers, which means that we can get our summary statistics. So this is where we have our summary statistics. The mean is 123.8 pounds with a standard deviation of 4.6043 pounds. And then for group 2, we can do the same thing. So no outliers, and then we can get our summary statistics here. Here's our X bar, and here's our standard deviation. So step 2 is to write out our hypotheses. So this is a two-sample mean problem, so we're comparing two means. So our null hypothesis is that mu1 equals mu2, meaning the mean breaking strengths are equal. And our alternative is mu1 is greater than mu2. Remember that the mean, or mu, represents the mean breaking strength, and the one at 2 weeks should have a greater breaking strength than the mean at 12 groups, since we think that the one, or 16 weeks, because the one at 16 weeks has decayed more, meaning it would take less strength to break them. So that's why the symbol is a greater than symbol. All right, step 3, we're going to check our conditions. So because we have two different groups, we do need to check our conditions for both groups. So for the independent condition, big N is all strips of polyester. That's greater than 10 times 5. That's reasonable to assume for both groups, since our sample size is 5 in both groups. It's reasonable to assume that there's more than 50 strips of polyester. The normal quantile plot is roughly linear for both. So we can see that by looking at our graphs here. So here's a normal quantile plot for the first one. And here's a normal quantile plot for the second one. So roughly linear for both. And the random condition is stated that they were randomly assigned. All right, in terms of our calculation, this is our test statistic. So we're just going to do x bar 1 minus x bar 2 over the square root of the standard deviation of the first group squared over n1. And, this should say a 2 here. Standard deviation of the second group squared over n2. So plugging in our values that we identified in step 1, we get a test statistic of 0.989. In terms of degrees of freedom, since we have two groups, we're going to take the smaller of the two samples. So since they're both 5, our degrees of freedom are going to be 4. So looking at our t-table, degrees of freedom is 4, and our test statistic is between 0.941 and 1.19, which means our p-value is between 0.15 and 0.20. So lastly, for our interpretation and context, we're going to say since our p-value is between 0.15 and 0.20, this is greater than alpha of 0.05. We fail to reject our null hypothesis. We do not have enough evidence to show that polyester decays more in 16 weeks than in 2 weeks. All right, so now let's look at a comparing two proportions example. It says Time Magazine reported the result of a telephone poll of a random sample of 800 adult Americans. Question posed was, should the federal tax on cigarettes be raised to pay for healthcare reform? The results showed that 351 of 605 non-smokers said yes, and 90 of 195 smokers said yes. Is there significant evidence at the alpha of 0.05 level to conclude that the two populations differ significantly with respect to their opinions? All right, so again, step 1, we're going to identify our symbols. We have two populations, so we have two sets of symbols. So our first group are smokers. And there are 605 non-smokers. And to calculate the sample proportion of that group, we're going to do 351 over 605. That's 0.58. In our second group, we have smokers. So that's a total of 195. And the sample proportion is 90 over 195, which is 0.46. The next thing we have is the combined sample proportion. So this is something that we're going to use in our conditions and calculations. What it is basically if we were to put all these people together into one group, what would be the proportion of people who say yes? So we're going to add together the people who said yes for smokers and non-smokers, and then the total number. So that's 441 over 800. So in total, 55% of people who were surveyed, regardless of whether they were smokers or non-smokers, think that the federal tax on cigarettes should be raised to pay for healthcare reform. All right, so for our hypotheses, this is a two sample proportion. It's two samples because I'm comparing smokers and non-smokers, and it's proportions because this data is categorical, right? We're counting the portion of people who say yes. So our null hypothesis is P1 equals P2, and our alternative is P1 does not equal P2 because it says differ significantly, so it doesn't indicate a direction. So P1 is the proportion of non-smokers who think tax on cigarettes should be raised to pay for healthcare reform. P2 is the proportion of smokers who think that tax cigarettes should be raised to pay for healthcare reform. All right, here are the conditions. So this is where we're going to use our combined sample proportion. But for the independent condition, it's the same, but we're going to check for both populations. So big N is all non-smokers. That's greater than or equal to 6,050. That's reasonable to assume. And big N, all smokers, is greater than 1,950. That's also reasonable to assume. So that condition is met. For the normal condition, we need to check for both samples, and the P hat that we're using is our combined proportion, which is the 0.55. So 605 times 0.55, that's 333, that's greater than or equal to 10, and then we check the other one, and then we check our other group. So then we do 195 times 0.55 and 195 times 1 minus 0.55. In both cases, all are greater than or equal to 10, so the normal condition is met. We know that they're approximately normal. Random is stated. It does say, where does it say? Random sample of 800 adult Americans. Okay. So in terms of the calculations, this is the calculations for a two sample proportion. We're going to subtract our P hats and then divide it by this. So plugging in our values from step 1, we get a test statistic of 2.93. There should be parentheses here, 2.93. And since this is Z, since we're dealing with proportions, we're going to find our p-value the same way we did before. So remember that since we are looking for a not equal to symbol, we know we're going to look at the negative side and double it. So we're going to look at negative 2.93. That's 0.0017, and we're going to double that. So 2 times 0.0017 is 0.0034. So lastly, our conclusion, since our p-value 0.0034 is less than alpha of 0.05, we reject our null hypothesis. We have statistically significant evidence that the proportion of non-smokers who think that the federal tax on cigarettes should be raised to pay for healthcare reform differs from the proportion of non-smokers.